Welcome back for the second installment of the AP Chemistry Chapter 16 Precipitation Equilibrium Problem Set. Let's take a look at problem number 19. In problem 19, you're asked to calculate the KSP given some molar solubilities. So you're told that the molar solubility of zinc carbonate is 1.21 times 10 to the negative fifth. We refer to molar solubilities as S variable-wise, and it's how many moles are soluble in a given liter. So we assume that the molar solubility is based on the coefficients, and since in our equation here everything is a coefficient of 1, if the solubility of zinc carbonate is 1.21 times 10 to the negative fifth, then we can call each of these positions S, S, and S 1.21 times 10 to the negative fifth. You write your KSP expression still disregarding the solid substance not showing up in your denominator of the KSP expression, and then you plug in S and S into the positions for the zinc concentration and the carbonate concentration. So you end up with essentially S squared, and since we know the S value, 1.21 times 10 to the negative fifth, we plug in that value and square it, and our KSP is 1.46 times 10 to the negative 10th. Part B, similar process, but now we're dealing with a substance that has 2 silver ions per 1 sulfate. So we're given the molar solubility of 0.014 molar. Again, we denote our molar solubilities with S, but now the silver ion has to be shown as 2S. Write our KSP expression, plug in our 2S for the silver ion concentration and our S for the sulfate ion concentration. We have the molar solubility as 0.014 molar, so this concentration of silver becomes 0.028 molar, still for the sulfate 0.014. Plug, solve, and our KSP is 1.1 times 10 to the negative fifth. For part C, similar process, similar procedure, but now we're dealing with 2 of our ions having molar solubilities that aren't just plain S. There's 3 strontiums for every 2 phosphates. Write our KSP expression. 3 shows up as our power for the strontium, 2 shows up as the superscript, the power for the phosphate. Plug in our 3S for the strontium, our 2S for the phosphate, and since we know what the molar solubility is, we plug in that value and solve out and get 1.1 times 10 to the negative 31. Let's take a look at problem 23. In problem 23, you're told you have a saturated solution of lead azide, PBN32. It's made by dissolving 25 milligrams in 100 milliliters of solution. You're asked to find what the KSP is. So to find the KSP, you got to know the concentration of lead and then also the azide. So you convert your 25 milligrams through grams and milligrams and then through moles to find out what the molar solubility is, and you get 8.3 times 10 to the negative fourth molar. Then you can calculate your KSP. This is just like the previous problem where you write out your expression and you assume lead is an S. And the azide is 2S because there's 2 azides for every lead. Write your KSP expression, plug in your S values. You know what the molar solubility is. We found it up here in this number 1 piece. And plug it in and solve and get your KSP to be 2.5 times 10 to the negative 9th. Problem 29. In problem 29, you're told that you dissolve some barium hydroxide in 100 milliliter solution, and then at equilibrium you're able to get 2.37 grams into the solution, and it has a pH of 13.28. You're asked to then calculate the KSP of BaOH2. To calculate KSP, you must know the concentration of the barium ions and also the hydroxide ions. So calculate first the concentration of the barium ions. Use mole to mass ratios and find out that since you have 100 milliliters, that you'll have a 0.138 molar solution of the barium ion. The hydroxide ion, a little easier as long as you remember some stuff from the previous couple of chapters, 13 and 14. If the pH is 13.28, you can find the pOH, and from the pOH you can find the concentration of the OH ions, and then you just plug in your values. Since you know the concentration of the hydroxide, that drops right in here. We found in the number 1 on the previous slide the concentration of the barium, as found here in number 1, you can just plug in your total values and get a KSP of 5.0 times 10 to the negative third.